Hi, and welcome to this session on the 2D frame analysis module. If you have not been following the sequence of videos, we're up to the point now where we'll discuss boundary conditions and member end fixities. Now, this is an interesting topic because it hits on some of the fundamental requirements of a stiffness analysis. It also has a great deal of influence on the behavior of the model. So the first thing that I'd like to point out is that boundary restraints and member end conditions kind of work hand in glove because they are both places where fixities or releases come together and potentially introduce hinges or break the continuity of moment flow in a structure. The other thing that I would point out is that if you're ever in doubt as to what the right thing is to do, I'm now showing a view of our frequently asked questions document, which is available online. And I just want to point out that in the section on calculation modules in the 2D frame analysis category, we have a topic called assigning proper fixities, where we actually show a document that gets into very specific detail, such as how should I set the fixities in a model that represents a truss with pinned joints, or how should I set fixities in a moment frame model with fixed bases. So feel free to take a look at this because this will give you a great deal of detail on how you can actually set boundary restraints and member end conditions for very specific situations. What we'll do in this case is just take an example of a braced frame, and we'll use the assumption that we want our column bases to be pinned. We'll also assume that we want the beam to column connections to be pinned, and we'll assume that the brace connections to the gussets are to be pinned as well. So we have, in a sense, no conditions anywhere in this model where we want to have moment transferred. Now what we'll do is we'll start here on the Joints and Loads tab, Joint Data subtab, and the first thing that we're going to do is we're going to establish our boundary restraints. These are our support conditions. When working with boundary restraints and member end conditions, we need to think of basically two things. One, we have a desire to model this structure in a way that we feel best represents the physical response that the structure will exhibit when it's subjected to the loads that we're about to apply to it. And two, we have an absolute mathematical need to guarantee stability to all of the joints in the model, or else the model won't run. We won't be able to analyze it at all. It gets interesting at times because there, in certain situations, are more than one way to ensure that stability and to achieve that desired behavior by a combination of fixities, member end fixities, and boundary restraints. We'll take a look at this example now, and what we'll do is understand that the need for stability of all of the joints is going to dictate that we come into this model and set all of the boundary restraints for moment about the z-axis, the axis that's perpendicular to the plane of the frame, to fixed. And the reason for that is because we've already established that all of the members will want to be pinned at all of the locations where they connect to joints. So that starts to dictate to us that an effective way to model that situation is to use member end releases or pinned member end conditions where the members connect to the joints. Now, if we have both pinned members connecting to joints and if we have joints that are free, then we have over-released those joints. There's absolutely no connection either to ground or to members with a measurable stiffness for those moments at those joints to be transferred anywhere. They basically, the joints just spin, and that is not a situation that the analysis module can handle. So what we'll do in this situation to ensure stability of the nodes is we're just going to use fixed about the z-axis conditions for all 4 of the nodes in this model. Those nodes will not be able to rotate about the z-axis, but again, we'll take care of the hinges or the pinned conditions of the member ends when we move on to member end conditions. Now, in addition to establishing the z rotational degrees of freedom, we also need to satisfy stability in the x and the y direction, and we'll do that at nodes number 1 and number 4 by indicating that we want node number 1 to be fixed against translation in the x or the left to right direction, and fixed against translation in the y or up and down direction. And the same settings hold true for the other lower node, which is node number 4. So we'll say node number 4 is to be fixed against translation in both the x and the y directions. Okay, so at this point, we have correctly established all of the boundary restraints for the 4 nodes in this model. Now what we'll do is move to the Members and Loads tab, Member Data subtab, and we need to pay some attention to the member end conditions at both the I end and the J end. This would be an ideal time for us to insert a short discussion on the member local coordinate system, because it's essential to understand that local coordinate system when discussing member end conditions. So what we have here is a diagram that's shown in the online help. It's in the 2D frame analysis section, and the subheading is members and member loads, where you'll find this diagram. This represents a joint. The big blue dot represents a joint, and then the green bar represents a member that frames into that joint. And what we're going to focus on is the bottom end of that member, where there's some discussion about the different releases. The thing that's important to understand about members is that there is a sense or an orientation or a coordinate axis system that's associated with those members, and it's set up on the basis of how we define the starting and ending nodes, that is the I and the J end nodes. So we can think of there being an x-axis that runs along the longitudinal direction of the member, and in particular it can be thought of as running from the I end to the J end. So the positive local x direction runs from I to J. There's also a member local z-axis, and it's fairly straightforward in this 2D plane frame environment. The member z-axis is the one that, for strong axis oriented members, which is typical, the member z-axis points out of the plane of the frame. There's a mathematical way to determine that z-axis, and it has to do with taking the vector cross product of the local x-axis crossed with the global y-axis. It's unnecessary to get into the details of it, though, in this 2D environment. All you need to remember is that the member z-axis is always the one that points out of the plane of the frame. And then finally, there's a member local y-axis, and again, there are mathematical rules that relate the x and the y and the z-axis, such that you can find the y-axis by crossing one vector into the other, but it's, again, overkill for the 2D environment. The thing that's important to understand is that when members are used in their strong axis orientation, the member y-axis is the one that is mutually perpendicular to the x and the z-axis. It'll be in the plane of the frame, and when you think in terms of a wide flange member, the member local y-axis is the one that is in the plane of the web of that member. So z is the strong axis of bending, y would be considered the weak axis of bending, and X you can think of as the longitudinal axis, or also a torsional axis if you want to regard it that way. Now in this situation, it's fairly straightforward because we decided that we wanted the beam to column connections to be modeled as pinned, and we wanted the end conditions of both braces to be modeled as pinned as well. So our job is easy in this case because all we need to do is work our way down the list of members and indicate that all Z end conditions for both the starting end and the ending end are to be modeled as pinned. So we've achieved stability of the nodes at the boundary conditions tab, and now we're achieving the desired response of the structure so that the members all act as simply supported or pinned by establishing the pinned setting for the Z degree of freedom, the bending moment about the axis perpendicular to the plane of the frame, for all of the members in the model. I would just add that we'll leave the X and Y direction degrees of freedom for both the I and the J end set to fixed for all members, and what that means is that all members are connected in a translational sense to their respective nodes, their end nodes. There's no slide plates, there's no slide bearings, there's no slip connections, there's nothing out of the ordinary like that. So at this point, now we have a model that correctly represents the behavior in terms of translational and rotational fixities and releases for the braced frame based on our design assumptions. The next step that we'll take a look at will continue in the next video, and that will be defining and assigning materials and sections. Thanks very much and have a great day.